You ever wondered if there's a perfect recipe for, well, for anything? What if I told you this secret to the most delicious, most cost-effective meatloaf isn't in some old cookbook, but is actually in a math equation? Let's dive in, because this simple butcher's problem unlocks a tool that's used by some of the biggest companies in the world.
Because that's the real question, right? Businesses deal with this every single day. They have to make the best thing they possibly can for you, the customer, but they also have to spend the least amount of money doing it. And the tool they use to crack that puzzle is a powerful branch of mathematics called optimization.
All right, to see exactly how this works, we're going to step inside the village butcher shop. Now, they have a classic problem on their hands. How do they mix their ground beef and ground pork to make a fantastic meatloaf that isn't too fatty and, this is the big one, costs them as little as possible to make?
Okay, so here are the hard numbers. We've got two ingredients. First, ground beef. It's 20% fat and costs 80 cents a pound. Then you've got the ground pork. It's a bit fattier, 32%, but it's cheaper at 60 cents a pound. Now, the butcher has two critical rules. Rule 1, the final 1 pound meatloaf can't be more than 25% fat. Rule 2, it has to be made for the absolute minimum cost. This is where the magic really starts. We are going to take this very real-world problem and translate it into the clean, precise language of mathematics. This whole process, it's called modeling, and it is the absolute heart of a field called operations research.
So, first things first. To turn this into a math problem, you have to name the things you're trying to figure out. In this case, it's pretty simple. How much beef and how much pork are we going to use? So let's give them names. We'll call the pounds of ground beef X1 and the pounds of ground pork X2.
Now, every single optimization problem has a goal, an objective. Are you trying to maximize your profit, make the most money possible? Or, like our butcher, are you trying to minimize your costs, spend the least money possible? We capture this main goal in one single equation, and it's called the objective function.
For our butcher, the equation is pretty straightforward. The total cost, which we'll just call Z, is simply 80 cents times the amount of beef we use, plus 60 cents times the amount of pork. Our mission, then, is to make the value of Z as small as it can possibly be. That's it. That is our objective function.
But hold on. If pork is cheaper, why not just make the entire meatloaf out of pork? Because of the rules. Remember, it can't be too fatty. In math, these rules are called constraints. You can think of them as the rules of the game. They're the boundaries we have to operate within.
Let's break those rules down into math. First up, fat content. The fat from the beef, that's 0.20 times x1, plus the fat from the pork, 0.32 times x2. All of that together has to be less than or equal to 0.25 pounds. Okay. Second, total weight. That's easy. The pounds of beef plus the pounds of pork has to equal exactly 1. And finally, a rule that's so obvious we might forget it, but math needs us to be clear, you can't use a negative amount of meat, right? So both x1 and x2 have to be 0 or more.
Okay, so we've got our equations. And now we can do something really, really cool. We can actually draw a map of every single possible recipe that follows the butcher's rules. This whole visual approach is called the graphical method.
It's really just a 3-step process. We're going to plot our rules, our constraints, as lines on a graph. Then, we find the area where all of those rules are true at the same time. We call this the feasible region. And here's the incredible shortcut that makes this all work. The perfect optimal solution is always hiding at one of the corners of this region. We just have to check the corners.
All right, let's actually plot this out. The horizontal axis is our pounds of beef, the vertical is pounds of pork. Our first rule, that the weight adds up to 1, gives us this straight line. Any point on it is a 1-pound mix. Our second rule, the fat constraint, gives us the second line. Now, since the fat has to be less than or equal to 25%, we're only interested in the area below this line. The only place where both rules are true at the same time is this highlighted segment right here. This is our feasible region. Every single point on this little line is a valid meatloaf recipe.
So we have our map of all the possible recipes that are allowed, but which one is the absolute cheapest? To figure that out, we need to bring our objective function, that cost equation, back into the picture. Okay, now think about that cost equation as its own line on the graph. We can slide this cost line up and down. Since we want to find the lowest possible cost, we want to push that line as far down as it can go while still just barely touching our feasible region. And watch. The very last point it touches, right there. That is our optimal solution. It's the cheapest recipe that still follows all the rules, and it lands right at the intersection of our two constraint lines. And by solving for where those two lines cross, we get the exact answer. The perfect recipe needs 7/12ths of a pound of ground beef and 5/12ths of a pound of ground pork. Or, roughly 0.58 pounds of beef and 0.42 pounds of pork. And when we plug those amounts back into our cost equation, we get the payoff. We find the absolute lowest possible cost for 1 pound meatloaf that meets the fat requirement, just under 72 cents. Any other combination is either going to be too fatty or it's going to be more expensive. That's the best you can do. So we solved the butcher's problem. But the real power of this technique, it's called linear programming, isn't just about meatloaf. It is a cornerstone of a field called operations research, which is all about using science to make better decisions in huge, complex systems. This same mathematical logic, just scaled up with computers, is used to solve enormous problems. Companies use it to figure out the most profitable mix of products to make in a factory. Airlines use it to create the most efficient shipping schedules. It's used to allocate multi-million-dollar advertising budgets, even to create optimal staffing schedules in a hospital. I love this quote because it really captures the scale of it all. It's not just solving little puzzles. It's a scientific attack on the complex problems that come up when you're managing huge systems of people, machines, materials, and money. It's all about finding that single best way forward when you've got countless options and just as many rules. So the next time you're facing a complex choice with a lot of trade-offs, maybe it's planning a budget, maybe it's just a project at work, remember the butcher's meatloaf. You might just be looking at an optimization problem in disguise, just waiting for the right set of equations to unlock the perfect solution. Makes you wonder, doesn't it? What will you optimize?